Hi guys, welcome to the thermochemistry part of our little 5-minute film festival. So when you see thermochemistry, please do not run for the hills. It is actually pretty much logical in a lot of formulas. So the first thing I did was forms of energy. So energy is the ability to do work. We have potential energy next, and it is the energy due to position, composition, or arrangement. It is also the energy associated with forces of attraction and repulsion between objects, or in this case atoms. Any object that is lifted from its resting position has potential energy because it has the potential to do work when released. For example, when the ball is released from the top of the hill, it is pulled down by gravity, and the potential energy is converted to kinetic energy, or the energy of motion, during the fall. Now over here, remember that kinetic energy is equal to 1/2 mass times velocity squared. This diagram here shows the energy for two hydrogen atoms as a function of the distance between them. Notice that to the right side, when the two hydrogen atoms are very far apart, they're not very attracted to each other, while when they're pushed very close together, they're going to be very repulsive at short distances. You're looking for the lowest potential energy, which often happens in the Goldilocks region. Heat is not a thing. It is a process. It depends on the speed of the particles, the number of particles, their mass, and the type of particles in an object. Temperature, on the other hand, does not depend on the size or type of the object. So the temperature of this small cup of water may be the exact same as the temperature of this large bathtub of water, but the tub actually has more heat because it has more thermal energy overall. Enthalpy is the change in heat of a system under constant pressure conditions. It is a state function, meaning that its value is independent of the path of the system to reach that point. We have two more diagrams here. And then in this top diagram, you can see that the reaction is exothermic, meaning that heat is leaving the system for the surroundings. The products of this reaction are more stable than the reactants because they have a lower potential energy. Now down here you can see it's an endothermic reaction in which heat is entering the system from the surroundings, and this will actually feel cold to the touch. In addition, the products, which are actually up here, have more potential energy. I am so sorry. They are unstable. They have more potential energy than the reactants do. Now this diagram here illustrates the first law of thermodynamics in that it shows the energy of the system plus the energy of the surroundings is always equal to a constant energy of the universe. While energy can be degraded, like being released as heat, the total amount always remains the same. In the second law of thermodynamics, it says that changes in entropy of the universe can never be negative. This is why no matter how much I decide to clean my room, it always becomes messy again in the future. Now we have our first practice problem with work, and we are looking for how much work the system does when it expands from 2 to 5 liters at a constant pressure. Now work should be a negative value here. We have our favorite formula. Work is negative P delta V. So we're going to calculate delta V by saying it's the final minus the initial, or 5 minus 2, which gives you 3. In addition, you have to convert your millimeters of mercury to atmospheres. And once you have your pressure and your change in volume, you simply multiply them together, and you multiply them by -1, and you get negative 2.96 liter atmospheres. Our next problem deals with change in enthalpy as well as energy. So one equation that relates these two is on the first line. Delta H is equal to delta E plus P delta V. And this part should be very, very, very close to what you consider work right off the top of your head. So from the problem, we actually know that the value of delta E is negative 100 kilojoules, and it says that the value of the work is 10 kilojoules. So you should be able to notice that that should go right there. If you plug the 2 in, you simply pop out a negative 90 kilojoules, and that is your delta H value. And since it's negative, you know that this is an exothermic reaction, so energy is being released. Finally, we have an entropy problem asking for the overall change during the reaction. And we are given a nice VCE, as well as values for all these different chemical species. So this can be modeled by the summation of the products minus the summation of the reactants from our VCE. Using the given values in the problem, the value of delta S is positive, indicating an increase in entropy. So what they did here is they summed all the reactants first, and then they summed all the products, and then they simply went 622.7, the products, minus 442.8, the reactants. And I would advise doing this in that sometimes it's hard to keep it all in one giant equation rather than separating them. And notice that your units for entropy are joules per Kelvin. And once again, since this number is positive, the products are more random and disorderly than the reactants. And one thing is, if you look back here, you really couldn't have guessed whether the products or the reactants were was going to have more entropy, because you see 3 moles of gas and 3 moles of gas. So I just want to thank you all for watching my video, and good luck with all your AP exams.